This is a photo of a car mechanic's shop. There are 3 United States Postal Services trucks being serviced, and 1 not being serviced. Figure 12. 1 linear regression and correlation can help you determine if an auto mechanic's salary is related to his work experience. Credit, modification of work. USPS commissions local repair shop for some needed work on its older trucks. By Joshua Rothhaus/Flickr, CC by 2. 0. Chapter objectives. By the end of this chapter, the student should be able to discuss basic ideas of linear regression and correlation, create and interpret a line of best fit, calculate and interpret the correlation coefficient, calculate and interpret outliers. Professionals often want to know how 2 or more numeric variables are related. For example, is there a relationship between the grade on the second math exam a student takes and the grade on the final exam? If there is a relationship, what is the relationship and how strong is it? In another example, your income may be determined by your education, your profession, your years of experience, and your ability. The amount you pay a repair person for labor is often determined by an initial amount plus an hourly fee. The type of data described in the examples is bivariate data, bi for 2 variables. In reality, statisticians use multivariate data, meaning many variables. In this chapter, you will be studying the simplest form of regression, linear regression, with 1 independent variable x. This involves data that fits a line in 2 dimensions. You will also study correlation, which measures how strong the relationship is. Linear regression for 2 variables is based on a linear equation with 1 independent variable. The equation has the form letter 1 d466 equals letter 1 d440 plus bx, where a and b are constant numbers. The variable x is the independent variable, and y is the dependent variable. Typically, you choose a value to substitute for the independent variable and then solve for the dependent variable. Example 12. 1. The following examples are linear equations. Letter 1 d466 equals 3 plus 2x. Letter 1 d466 equals 0, 1 plus 1, 2x. Try it 12. 1. Is the following an example of a linear equation? Y equals 0. 125 3, 5x. The graph of a linear equation of the form y equals a plus bx is a straight line. Any line that is not vertical can be described by this equation. Example 12. 2. Graph the equation y equals 1 plus 2x. Graph of the equation y equals minus 1 plus 2x. This is a straight line that crosses the y-axis at and is sloped up and to the right, rising 2 units for every 1 unit of run. Figure 12.2. Try it 12.2. Is the following an example of a linear equation? Why or why not? This is a graph of an equation. The x-axis is labeled in intervals of 2 from 0 to 14. The y-axis is labeled in intervals of 2 from 0 to 12. The equation's graph is a curve that crosses the y-axis at 2 and curves upward and to the right. Figure 12. 3. Example 12. 3. A local small business completes federal tax returns for customers. The rate for services is $32 per hour plus a $31.51 time dollars charge. The total cost to a customer depends on the number of hours it takes to complete the job. Problem. Find the equation that expresses the total cost in terms of the number of hours required to complete the job. Try it 12. 3. Emma's Extreme Sports hires hang gliding instructors and pays them a fee of $50 per class as well as $20 per student in the class. The total cost Emma pays depends on the number of students in a class. Find the equation that expresses the total cost in terms of the number of students in a class. Slope and y-intercept of a linear equation. For the linear equation y equals a plus bx, b equals slope, and a equals y-intercept. From algebra, recall that the slope is a number that describes the steepness of a line, and the y-intercept is the y-coordinate of the point, 0. A, where the line crosses the y-axis. 3 possible graphs of the equation y equals a plus bx. For the first graph, A, b0, and so the line slopes upward to the right. For the second, b equals 0, and the graph of the equation is a horizontal line. In the third graph, C, b0, and the line slopes downward to the right. Figure 12. For 3 possible graphs of y equals a plus bx. A, if b0, the line slopes upward to the right. B, if b equals 0, the line is horizontal. C, if b0, the line slopes downward to the right. Example 12. 4. Svetlana tutors to make extra money for college. For each tutoring session, she charges a one-time fee of $25 plus $15 per hour of tutoring. A linear equation that expresses the total amount of money Svetlana earns for each session she tutors is y equals 25 plus 15x. Problem: what are the independent and dependent variables? What is the y-intercept and what is the slope? Interpret them using complete sentences. Solution: the independent variable x is the number of hours Svetlana tutors each session. The dependent variable y is the amount, in dollars, Svetlana earns for each session. The y-intercept is 25, equals 25. At the start of the tutoring session, Svetlana charges a one-time fee of $25. This is when x equals 0. The slope is 15b equals 15. For each session, Svetlana earns $15 for each hour she tutors. Try it 12. 4. Ethan repairs household appliances like dishwashers and refrigerators. For each visit, he charges $25 plus $20 per hour of work. A linear equation that expresses the total amount of money Ethan earns per visit is y equals 25 plus 20x. What are the independent and dependent variables? What is the y-intercept and what is the slope? Interpret them using complete sentences. Before we take up the discussion of linear regression and correlation, we need to examine a way to display the relation between two variables x and y. The most common and easiest way is a scatter plot. The following example illustrates a scatter plot. Example 12. 5. An educational researcher collects data on the vocabulary size of children as a function of age. The data is shown in Table 12. 1. Is there a relationship between age and vocabulary size for young children? Construct a scatter plot. Let x equals child's age and let y equals vocabulary size. Age years, vocabulary size number of words. 3 655, 4 1098, 6 2463, 7 3195. Table 12. 1. This is a scatter plot for the data provided. The x-axis represents the year and the y-axis represents the number of m-commerce users in millions. There are 4 points plotted at 2000, 0, 5, 2002, 20, 0, 2003, 33, 0, 2004, 47, 0, figure 12, 5. Using the T83, 83 plus 84, 84 plus calculator. To create a scatter plot, enter your x data into list L1 and your y data into list L2. Press second STATPLOT enter to use plot 1. On the input screen for plot 1, highlight on and press enter. Make sure the other plots are off. For type, highlight the very first icon, which is the scatter plot, and press enter. For X list, enter L1 enter, and for IList, L2 enter. For mark, it does not matter which symbol you highlight, but the square is the easiest to see. Press enter. Make sure there are no other equations that could be plotted. Press Y and clear any equations out. Press the zoom key and then the number 9 for menu item zoom stat. The calculator will fit the window to the data. You can press window to see the scaling of the axes. Try it 12. 5. Amelia plays basketball for her high school. She wants to improve to play at the college level. She notices that the number of points she scores in a game goes up in response to the number of hours. She practices her jump shot each week. She records the following data. X hours practicing jump shot, Y points scored in a game. 5:15, 7:22, 9:28, 10:31, 11:33, 12:36. Table 12. 2. Construct a scatter plot and state if what Amelia thinks appears to be true. A scatter plot shows the direction of a relationship between the variables. A clear direction happens when there is either high values of one variable occurring with high values of the other variable, or low values of one variable occurring with low values of the other variable. High values of one variable occurring with low values of the other variable. You can determine the strength of the relationship by looking at the scatter plot and seeing how close the points are to a line, a power function, an exponential function, or to some other type of function. For a linear relationship, there is an exception. Consider a scatter plot where all the points fall on a horizontal line, providing a perfect fit. The horizontal line would in fact show no relationship. When you look at a scatter plot, you want to notice the overall pattern and any deviations from the pattern. The following scatterplot examples illustrate these concepts. The first graph is a scatter plot with 6 points plotted. The points form a pattern that moves upward to the right, almost in a straight line. The second graph is a scatter plot with the same 6 points as the first graph. A 7th point is plotted in the top left corner of the quadrant. It falls outside the general pattern set by the other 6 points. Figure 12:6. The first graph is a scatter plot with 6 points plotted. The points form a pattern that moves downward to the right, almost in a straight line. The second graph is a scatter plot of 8 points. These points form a general downward pattern, but the points do not align in a tight pattern. Figure 12:7. The first graph is a scatter plot of 7 points in an exponential pattern. The pattern of the points begins along the x-axis and curves steeply upward to the right side of the quadrant. The second graph shows a scatter plot with many points scattered everywhere, exhibiting no pattern. Figure 12:8. In this chapter, we are interested in scatter plots that show a linear pattern. Linear patterns are quite common. The linear relationship is strong if the points are close to a straight line, except in the case of a horizontal line where there is no relationship. If we think that the points show a linear relationship, we would like to draw a line on the scatter plot. This line can be calculated through a process called linear regression. However, we only calculate a regression line if one of the variables helps to explain or predict the other variable. If x is the independent variable and y the dependent variable, then we can use a regression line to predict y for a given value of x. Data rarely fit a straight line exactly. Usually, you must be satisfied with rough predictions. Typically, you have a set of data whose scatter plot appears to fit a straight line. This is called a line of best fit or least squares line. Collaborative exercise. If you know a person's pinky, smallest, finger length, do you think you could predict that person's height? Collect data from your class pinky finger length in inches. The independent variable x is pinky finger length and the dependent variable y is height. For each set of data, plot the points on graph paper. Make your graph big enough and use a ruler. Then, by eye, draw a line that appears to fit the data. For your line, pick 2 convenient points and use them to find the slope of the line. Find the y-intercept of the line by extending your line so it crosses the y-axis. Using the slopes and the y-intercepts, write your equation of best fit. Do you think everyone will have the same equation? Why or why not? According to your equation, what is the predicted height for a pinky length of 25 inches? Example 12:6. A random sample of 11 statistics students produced the following data, where x is the third exam score out of 80, and y is the final exam score out of 200. Can you predict the final exam score of a random student if you know the third exam score? X third exam score, y final exam score. 65 175, 67 133, 71 185, 71 163, 66 126, 75 198, 67 153, 70 163, 71 159, 69 151, 69 159. Table 12. 3 tables showing the scores on the final exam based on scores from the third exam. This is a scatter plot of the data provided. The third exam score is plotted on the x-axis, and the final exam score is plotted on the y-axis. The points form a strong, positive, linear pattern. Figure 12. 9 scatter plots showing the scores on the final exam based on scores from the third exam. Try it 12. 6. Scuba divers have maximum dive times they cannot exceed when going to different depths. The data in Table 12. 4 show different depths with the maximum dive times in minutes. Use your calculator to find the least squares regression line and predict the maximum dive time for 110 feet. X, depth in feet. Y, maximum dive time. 50-80, 60-55, 70-45, 80-35, 90-25, 122. Table 12. 4. The third exam score, X, is the independent variable, and the final exam score, Y, is the dependent variable. We will plot a regression line that best fits the data. If each of you were to fit a line by I, you would draw different lines. We can use what is called a least squares regression line to obtain the best fit line. Consider the following diagram. Each point of data is of the form X, Y, and each point of the line of best fit using least squares linear regression has the form X, Y circumflex. The Y circumflex is red, Y hat, and is the estimated value of Y. It is the value of Y obtained using the regression line. It is not generally equal to Y from data. The scatter plot of exam scores with a line of best fit. One data point is highlighted along with the corresponding point on the line of best fit. Both points have the same x-coordinate. The distance between these 2 points illustrates how to compute the sum of squared errors. Figure 12. 10. The term y0, y circumflex 0 equals epsilon 0, is called the error or residual. It is not an error in the sense of a mistake. The absolute value of a residual measures the vertical distance between the actual value of y and the estimated value of y. In other words, it measures the vertical distance between the actual data point and the predicted point on the line. If the observed data point lies above the line, the residual is positive, and the line underestimates the actual data value for y. If the observed data point lies below the line, the residual is negative, and the line overestimates that actual data value for y in the diagram in Figure 12. 10. y0, y circumflex 0 equals epsilon 0 is the residual for the point shown. Here the point lies above the line, and the residual is positive. Epsilon equals the Greek letter epsilon. For each data point, you can calculate the residuals or errors. Y equals epsilon for I equals 1, 2, 3, 11. Each epsilon is a vertical distance. For the example about the third exam scores and the final exam scores for the 11 statistics students, there are 11 data points. Therefore, there are 11 epsilon values. If you square each epsilon and add, you get letter 1 D700, 1, 2 plus, letter 1 D700, 2, 2 plus, letter 1 D700, 11, 2 equals letter 1 D6F4, letter 1 D456 equals 111, letter 1 D700, 2. This is called the sum of squared errors, SSE. Using calculus, you can determine the values of A and B that make the SSE a minimum. When you make the SSE a minimum, you have determined the points that are on the line of best fit. It turns out that the line of best fit has the equation letter 1 D466 letter 2C6 equals letter 1 D44E plus letter 1 D44F letter 1 D465, where letter 1 D44E equals letter 1 D466 minus letter 1d44f letter 1d465. And letter 1d44f equals letter 1d6f4. Letter 1d465 minus letter 1d465. Letter 1d466 minus letter 1d466. Letter 1d6f4. Letter 1d465 minus letter 1d465, 2. The sample means of the x values, and the y values are letter 1d465 and letter 1d466, respectively. The best fit line always passes through the point letter 1d465, letter 1d466. The slope b can be written as letter 1d44f equals letter 1d45f. Letter 1d460, letter 1d466, letter 1d460, letter 1d465, where c equals the standard deviation of the y values, and sx equals the standard deviation of the x values. R is the correlation coefficient, which is discussed in the next section. Residuals plots. A residuals plot can be used to help determine if a set of x, y data is linearly correlated. For each data point used to create the correlation line, a residual y can be calculated, where y is the observed value of the response variable, and y is the value predicted by the correlation line. The difference between these values is called the residual. A residuals plot shows the explanatory variable x on the horizontal axis and the residual for that value on the vertical axis. The residuals plot is often shown together with a scatter plot of the data. While a scatter plot of the data should resemble a straight line, a residuals plot should appear random, with no pattern and no outliers. It should also show constant error variance, meaning the residuals should not consistently increase or decrease as the explanatory variable x increases. A residuals plot can be created using StatCrunch or a t-calculator. The plot should appear random. A box plot of the residuals is also helpful to verify that there are no outliers in the data. By observing the scatter plot of the data, the residuals plot, and the box plot of residuals, together with the linear correlation coefficient, we can usually determine if it is reasonable to conclude that the data are linearly correlated. Example: a shop owner uses a straight-line regression to estimate the number of ice cream cones that would be sold in a day based on the temperature at noon. The owner has data for a 2-year period and chose 9 days at random. A scatter plot of the data is shown, together with a residuals plot. Temperature degrees F ice cream cones sold: 70 105, 85 240, 65 49, 72 147, 80 231, 61 38, 75 193, 78 196, 68 89. Table 12. 5 tables showing the number of ice cream cones sold on 9 random days and the temperature at noon on those days. Scatter plot of ice cream sold against temperature of the given data. A straight line is constructed for the plot. Figure 12. 11 scatter plot of the data looks like a straight line. Residual plot of residuals against temperature of the given data. Figure 12. 12 residuals plot appears random. Least squares criteria for best fit. The process of fitting the best fit line is called linear regression. The idea behind finding the best fit line is based on the assumption that the data are scattered about a straight line. The criteria for the best fit line is that the sum of the squared errors, SSE, is minimized, that is, made as small as possible. Any other line you might choose would have a higher SSE than the best fit line. This best fit line is called the least squares regression line. Note: computer spreadsheets, statistical software, and many calculators can quickly calculate the best fit line and create the graphs. The calculations tend to be tedious if done by hand. Instructions to use the T83, T83+, and T84+ calculators to find the best fit line and create a scatter plot are shown at the end of this section. Third exam versus final exam example. The graph of the line of best fit for the third exam final exam example is as follows. The scatter plot of exam scores with a line of best fit. One data point is highlighted along with the corresponding point on the line of best fit. Figure 12.13. The least squares regression line, best fit line. For the third exam final exam example has the equation. Letter 1D466 letter 2C6 equals minus 173. 51 plus 4. 83x. Reminder. Remember, it is always important to plot a scatter diagram first. If the scatter plot indicates that there is a linear relationship between the variables, then it is reasonable to use a best fit line to make predictions for y given x within the domain of x values in the sample data, but not necessarily for x values outside that domain. You could use the line to predict the final exam score for a student who earned a grade of 73 on the third exam. You should not use the line to predict the final exam score for a student who earned a grade of 50 on the third exam, because 50 is not within the domain of the x values in the sample data, which are between 65 and 75. Understanding slope. The slope of the line, b, describes how changes in the variables are related. It is important to interpret the slope of the line in the context of the situation represented by the data. You should be able to write a sentence interpreting the slope in plain English. Interpretation of the slope. The slope of the best fit line tells us how the dependent variable y changes for every 1 unit increase in the independent x variable on average. Third exam versus final exam example. Slope. The slope of the line is b equals 483. Interpretation. For a 1-point increase in the score on the third exam, the final exam score increases by 483 points on average. Using the T83, 83 plus 84, 84 plus calculator. Using the linear regression t-test, lin-reg t-test. In the StatList editor, enter the x data in list L1 and the y data in list L2, paired so that the corresponding x, y values are next to each other in the lists. If a particular pair of values is repeated, enter it as many times as it appears in the data. On the Stat Tests menu, scroll down with the cursor to select the lin-reg t-test. Be careful to select lin-reg t-test, as some calculators may also have a different item called lin-reg t-int. On the lin-reg t-test input screen enter xlist, L1, illist, L2, freq. 1. On the next line at the prompt beta or row, highlight not equal to 0 and press enter. Leave the line for regec, blank. Highlight calculate and press enter. 1. Image of calculator input screen for lin-reg t-test with input matching the instructions above. 2. Image of corresponding output calculator output screen for lin-reg t-test. Output screen shows line 1. Lin-reg t-test. Line 2, y equals a plus bx. Line 3, beta does not equal 0 and rho does not equal 0. Line 4, t equals 2,657,560,155. Line 5, df equals 9. Line 6, a equals 173, 513,363. Line 7, b equals 4. 827,394,209. Line 8, S equals 16. 41,237,711. Line 9, R squared equals 4,396,930,1,104. Line 10, R equals 663,093,591. Figure 12.14. The output screen contains a lot of information. For now, we will focus on a few items from the output and will return later to the other items. The second line says y equals a plus bx. Scroll down to find the values a equals 173, 513, and b equals 482.73. The equation of the best fit line is y circumflex equals 173. 51 plus 483x. The two items at the bottom are R2 equals 0, 43,969, and R equals 0, 663. For now, just note where to find these values. We will discuss them in the next two sections. Graphing the scatter plot and regression line. We are assuming your X data is already entered in list L1, and your Y data is in list L2. Press second STATPLOT enter to use plot 1. On the input screen for plot 1, highlight on and press enter. For type, highlight the very first icon, which is the scatter plot, and press enter. Indicate XList, L1 and IList, L2. For mark, it does not matter which symbol you highlight. Press the zoom key and then the number 9 for menu item zoom stat. The calculator will fit the window to the data. To graph the best fit line, press the Y equals key and type the equation 173. 5 plus 4x into equation Y1. The X key is immediately left of the stat key. Press zoom 9 again to graph it. Optional. If you want to change the viewing window, press the window key. Enter your desired window using Xmin, Xmax, Imin, Imax. Note, another way to graph the line after you create a scatter plot is to use lin-reg-t-test. Make sure you have done the scatter plot. Check it on your screen. Go to lin-reg-t-test and enter the lists. At reg-ec, press VARS and arrow over to YVGRS. Press 1 for 1, function. Press 1 for 1, Y1. Then arrow down to calculate and do the calculation for the line of best fit. Press Y equals, you will see the regression equation. Press graph, the line will be drawn. The correlation coefficient R. Besides looking at the scatter plot and seeing that a line seems reasonable, how can you tell if the line is a good predictor? Use the correlation coefficient as another indicator, besides the scatter plot, of the strength of the relationship between X and Y. The correlation coefficient, R, developed by Carl Pearson in the early 1900s, is numerical and provides a measure of strength and direction of the linear association between the independent variable X and the dependent variable Y. The correlation coefficient is calculated as letter 1 D45F equals letter 1 D45B, letter 1 D6F4, letter 1 D465, letter 1 D466 minus letter 1 D6F4, letter 1 D465, letter 1 D6F4, letter 1 D466, letter 1 D45B, letter 1 D6F4, letter 1 D465, 2 minus letter 1 D6F4, letter 1 D465, 2 letter 1 D45B, letter 1 D6F4, letter 1 D466, 2 minus letter 1 D6F4, where n equals the number of data points. If you suspect a linear relationship between X and Y, then R can measure how strong the linear relationship is. What the value of R tells us. The value of R is always between 1 and plus 1. 1 less or equal to R less or equal to 1. The size of the correlation R indicates the strength of the linear relationship between X and Y. Values of R close to 1 or to plus 1 indicate a stronger linear relationship between X and Y. If R equals 0, there is likely no linear correlation. It is important to view the scatter plot, however, because data that exhibit a curved or horizontal pattern may have a correlation of 0. If R equals 1, there is perfect positive correlation. If R equals 1, there is perfect negative correlation. In both these cases, all of the original data points lie on a straight line. Of course, in the real world, this will not generally happen. What the sign of R tells us. A positive value of R means that when X increases, Y tends to increase, and when X decreases, Y tends to decrease. Positive correlation. A negative value of R means that when X increases, Y tends to decrease, and when X decreases, Y tends to increase. Negative correlation. The sign of R is the same as the sign of the slope, B, of the best fit line. Note, strong correlation does not suggest that X causes Y or Y causes X. We say, correlation does not imply causation. 3 scatter plots with lines of best fit. The first scatter plot shows points ascending from the lower left to the upper right. The line of best fit has positive slope. The second scatter plot shows points descending from the upper left to the lower right. The line of best fit has negative slope. The third scatter plot of points form a horizontal pattern. The line of best fit is a horizontal line. Figure 12. 15. A scatter plot showing data with a positive correlation. R1b, a scatter plot showing data with a negative correlation. 1R0c, a scatter plot showing data with zero correlation. R equals 0. The formula for R looks formidable. However, computer spreadsheets, statistical software, and many calculators can quickly calculate R. The correlation coefficient R is the bottom item in the output screens for the Lin-Reg-T test on the T83, T83 Plus, or T84 Plus calculator. See previous section for instructions. The coefficient of determination. The variable R2 is called the coefficient of determination and is the square of the correlation coefficient, but is usually stated as a percent rather than in decimal form. It has an interpretation in the context of the data. R2, when expressed as a percent, represents the percent of variation in the dependent predicted variable y that can be explained by variation in the independent explanatory variable x using the regression best fit line. 1R2, when expressed as a percentage, represents the percent of variation in y that is not explained by variation in x using the regression line. This can be seen as the scattering of the observed data points about the regression line. Consider the third final exam example introduced in the previous section. The line of best fit is y circumflex equals 173, 51 plus 483x. The correlation coefficient is R equals 0, 6631. The coefficient of determination is R2 equals 0, 66,312 equals 0, 4397. Interpretation of R2 in the context of this example. Approximately 44% of the variation, 0. 4397, is approximately 0.44. In the final exam, grades can be explained by the variation in the grades on the third exam, using the best fit regression line. Therefore, approximately 56% of the variation, 1044 equals 0.56. In the final exam, grades cannot be explained by the variation in the grades on the third exam, using the best fit regression line. This is seen as the scattering of the points about the line. The correlation coefficient, R, tells us about the strength and direction of the linear relationship between x and y. However, the reliability of the linear model also depends on how many observed data points are in the sample. We need to look at both the value of the correlation coefficient R and the sample size n together. We perform a hypothesis test of the significance of the correlation coefficient to decide whether the linear relationship in the sample data is strong enough to use to model the relationship in the population. The sample data are used to compute R, the correlation coefficient for the sample. If we had data for the entire population, we could find the population correlation coefficient. But because we have only sample data, we cannot calculate the population correlation coefficient. The sample correlation coefficient, R, is our estimate of the unknown population correlation coefficient. The symbol for the population correlation coefficient is rho, the Greek letter rho. Rho equals population correlation coefficient, unknown. R equals sample correlation coefficient, known. Calculated from sample data. The hypothesis test lets us decide whether the value of the population correlation coefficient rho is close to 0 or significantly different from 0. We decide this based on the sample correlation coefficient R and the sample size n. If the test concludes that the correlation coefficient is significantly different from 0, we say that the correlation coefficient is significant. Conclusion. There is sufficient evidence to conclude that there is a significant linear relationship between x and y because the correlation coefficient is significantly different from 0. What the conclusion means. There is a significant linear relationship between x and y. we can use the regression line to model the linear relationship between X and Y in the population. If the test concludes that the correlation coefficient is not significantly different from 0, it is close to 0, we say that correlation coefficient is not significant. Conclusion. There is insufficient evidence to conclude that there is a significant linear relationship between X and Y because the correlation coefficient is not significantly different from 0. What the conclusion means. There is not a significant linear relationship between X and Y, therefore. We cannot use the regression line to model a linear relationship between X and Y in the population. Note if R is significant and the scatter plot shows a linear trend. The line can be used to predict the value of Y for values of X that are within the domain of observed X values. If R is not significant or if the scatter plot does not show a linear trend, the line should not be used for prediction. If R is significant and if the scatter plot shows a linear trend, the line may not be appropriate or reliable for prediction outside the domain of observed X values in the data. Performing the hypothesis test. Null hypothesis. H0. Rho equals alternate hypothesis. Rho not equal to what the hypotheses mean in words. Null hypothesis H0. The population correlation coefficient is not significantly different from 0. There is not a significant linear relationship, correlation between X and Y in the population. Alternate hypothesis. The population correlation coefficient is significantly different from 0. There is a significant linear relationship, correlation, between X and Y in the population. Drawing a conclusion. There are two methods of making the decision. The two methods are equivalent and give the same result. Method 1. Using the p-value. Method 2. Using a table of critical values. In this chapter of this textbook, we will always use a significance level of 5%, alpha equals 0. 5. Note, using the p-value method, you could choose any appropriate significance level you want. You are not limited to using alpha equals 0. 5. But the table of critical values provided in this textbook assumes that we are using a significance level of 5%, alpha equals 0. 5. If we wanted to use a different significance level than 5% with the critical value method, we would need different tables of critical values that are not provided in this textbook. Method 1. Using a p-value to make a decision using the T83, 83 plus, 84, 84 plus calculator to calculate the p-value using Lin-Reg t-test. On the Lin-Reg t-test input screen, on the line prompt for beta or rho, highlight, not equal to, the output screen shows the p-value on the line that reads p equals. Most computer statistical software can calculate the p-value. If the p-value is less than the significance level alpha equals 0.5, decision, reject the null hypothesis. Conclusion. There is sufficient evidence to conclude that there is a significant linear relationship between X and Y, because the correlation coefficient is significantly different from 0. If the p-value is not less than the significance level alpha equals 0.5, decision, do not reject the null hypothesis. Conclusion. There is insufficient evidence to conclude that there is a significant linear relationship between X and Y because the correlation coefficient is not significantly different from 0. Calculation notes. You will use technology to calculate the p-value. The following describes the calculations to compute the test statistics and the p-value. The p-value is calculated using a t-distribution with n2 degrees of freedom. The formula for the test statistic is letter 1d461 equals letter 1d45f letter 1d45b minus 2 square root 1 minus letter 1d45f 2 square root. The value of the test statistic, t, is shown in the computer or calculator output along with the p-value. The test statistic t has the same sign as the correlation coefficient r. The p-value is the combined area in both tails. An alternative way to calculate the p-value p given by lin-reg t-test is the command 2 *tcdf, abs t, 1099, n2 in second distr. Third exam versus final exam example. P-value method, consider the third exam final exam example. The line of best fit is y circumflex equals minus 173, 51 plus 483x with r equals 0. 6631, and there are n equals 11 data points. Can the regression line be used for prediction? Given a third exam score, x value, can we use the line to predict the final exam score, predicted y value? H0, rho equals ha, rho not equal to alpha equals 0. 5. The p-value is 0.26 from lin-reg t-test on your calculator or from computer software. The p-value, 0.26, is less than the significance level of alpha equals 0.5. Decision. Reject the null hypothesis H0 conclusion. There is sufficient evidence to conclude that there is a significant linear relationship between the third exam score x and the final exam score y because the correlation coefficient is significantly different from 0. Because r is significant and the scatter plot shows a linear trend, the regression line can be used to predict final exam scores. Method 2. Using a table of critical values to make a decision, the 95% critical values of the sample correlation coefficient table can be used to give you a good idea of whether the computed value of r is significant or not. Compare r to the appropriate critical value in the table. If r is not between the positive and negative critical values, then the correlation coefficient is significant. If r is significant, then you may want to use the line for prediction. Example 12. 7. Suppose you computed r equals 0, 801 using n equals 10 data points. df equals n2 equals 10, 2 equals 8. The critical values associated with df equals 8 are 632 and plus 0, 632. If r negative critical value or r positive critical value, then r is significant. Since r equals 0, 801 and 0, 801, 0, 632, r is significant and the line may be used for prediction. If you view this example on a number line, it will help you. Horizontal number line with values of minus 1, 632, 0, 0, 632, 0, 801, and 1 a dashed line above values. 632, 0, and 0. 632 indicates not significant values. Figure 12. 16r is not significant between minus 0, 632 and plus 0, 632. R equals 0. 801 plus 0, 632. Therefore, r is significant. Try it 12. 7. For a given line of best fit, you computed that r equals 0. 6501 using n equals 12 data points and the critical value is 0. 576. Can the line be used for prediction? Why or why not? Example 12. 8. Suppose you computed r equals 0, 624 with 14 data points. df equals 14, 2 equals 12. The critical values are 0, 532 and 0, 532. Since 0, 624, 0, 532, r is significant and the line can be used for prediction horizontal number line with values of minus 0, 624 minus 0, 532 and 0, 532, figure 12. 17 r equals 0, 624, 532. Therefore, r is significant. Try it 12. 8. For a given line of best fit, you compute that r equals 0. 5204 using n equals 9 data points and the critical value is 0. 666. Can the line be used for prediction? Why or why not? Example 12. 9. Suppose you computed r equals 0, 776 and n equals 6. df equals 62 equals 4. The critical values are 0,811 and 0,811. Since 0,811 0, 776 0, 811 R is not significant and the line should not be used for prediction. Horizontal number line with values 924 minus 0, 532 and 0, 532, figure 12, 18 minus 0, 811 R equals 0, 776 0, 811. Therefore, R is not significant. Try it 12. 9 for a given line of best fit. You compute that R equals 0. 7204 using n equals 8 data points, and the critical value is equals 0, 707. Can the line be used for prediction? Why or why not? Third exam versus final exam example. Critical value method. Consider the third exam final exam example. The line of best fit is y circumflex equals 173. 51 plus 483x with r equals 0, 6631, and there are n equals 11 data points. Can the regression line be used for prediction? Given a third exam score x value, can we use the line to predict the final exam score predicted y value? H0, rho equals ha, rho not equal to alpha equals 0. 5. Use the 95% critical value table for R with df equals n, 2 equals 11, 2 equals 9. The critical values are 0, 602, and plus 0. 602 since 0. 6631, 0, 602, R is significant. Decision. Reject the null hypothesis. Conclusion. There is sufficient evidence to conclude that there is a significant linear relationship between the third exam score x and the final exam score y because the correlation coefficient is significantly different from 0. Because R is significant and the scatter plot shows a linear trend, the regression line can be used to predict final exam scores. Example 12. 10. Suppose you computed the following correlation coefficients. Using the table at the end of the chapter, determine if R is significant and the line of best fit associated with each R can be used to predict a Y value. If it helps, draw a number line. R equals 0. 567 and the sample size n is 19. The df equals n, 2 equals 17. The critical value is 0, 456, 0, 567, 0. 456, so R is significant. R equals 0, 708 and the sample size n is 9. The df equals n, 2 equals 7. The critical value is 0, 666, 0. 708, 0. 666, so R is significant. R equals 0, 134 and the sample size n is 14. The df equals 14, 2 equals 12. The critical value is 0. 532, 0, 134 is between 0, 532 and 0, 532, so R is not significant. R equals 0 and the sample size n is 5. No matter what the DFS are, R equals 0 is between the two critical values, so R is not significant. Try it 12. 10. For a given line of best fit, you compute that R equals 0 using n equals 100 data points. Can the line be used for prediction? Why or why not? Assumptions in testing the significance of the correlation coefficient testing. The significance of the correlation coefficient requires that certain assumptions about the data are satisfied. The premise of this test is that the data are a sample of observed points taken from a larger population. We have not examined the entire population because it is not possible or feasible to do so. We are examining the sample to draw a conclusion about whether the linear relationship that we see between x and y in the sample data provides strong enough evidence so that we can conclude that there is a linear relationship between x and y in the population. The regression line equation that we calculate from the sample data gives the best fit line for our particular sample. We want to use this best fit line for the sample as an estimate of the best fit line for the population. Examining the scatter plot and testing the significance of the correlation coefficient helps us determine if it is appropriate to do this. The assumptions underlying the test of significance are: the relationship between the variables being correlated should be linear. The data points should fall along an approximate straight line pattern when plotted as x, y data points on a scatter plot. The y values for any particular x value are normally distributed about the line. This implies that there are more y values scattered closer to the line than are scattered farther away. Assumption 1 implies that these normal distributions are centered on the line. The means of these normal distributions of y values lie on the line. The standard deviations of the population y values about the line are equal for each value of x. In other words, each of these normal distributions of y values has the same shape and spread about the line. The residual errors are mutually independent, no pattern. The data are produced from a well-designed, random sample or randomized experiment. The left graph shows 3 sets of points. Each set falls in a vertical line. The points in each set are normally distributed along the line. They are densely packed in the middle and more spread out at the top and bottom. A downward sloping regression line passes through the mean of each set. The right graph shows the same regression line plotted. A vertical normal curve is shown for each line. Figure 12. 19. The y values for each x value are normally distributed about the line with the same standard deviation. For each x value, the mean of the y values lies on the regression line. More y values lie near the line than are scattered further away from the line. Recall the third final exam example. We examined the scatter plot and showed that the correlation coefficient is significant. We found the equation of the best fit line for the final exam grade as a function of the grade on the third exam. We can now use the least squares regression line for prediction. Suppose you want to estimate, or predict, the mean final exam score of statistics students who received 73 on the third exam. The exam scores, x values, range from 65 to 75. Since 73 is between the x values 65 and 75, substitute x equals 73 into the equation. Then, letter 1D466 letter 2C6 equals minus 173. 51 plus 4. 83. 73 equals 179. 8. We predict that statistics students who earn a grade of 73 on the third exam will earn a grade of 179. 8 on the final exam on average. Example 12. 11. Recall the third exam final exam example. Problem A. What would you predict the final exam score to be for a student who scored a 66 on the third exam? B. What would you predict the final exam score to be for a student who scored a 90 on the third exam? Solution A. 145. 27. B. The x values in the data are between 65 and 75. 90 is outside of the domain of the observed x values in the data, independent variable. So you cannot reliably predict the final exam score for this student. Even though it is possible to enter 90 into the equation for x and calculate a corresponding y value, the y value that you get will not be reliable. To understand really how unreliable the prediction can be outside of the observed x values observed in the data, make the substitution x equals 90 into the equation. Letter 1D466 letter 2C6 equals 173. 51 plus 4. 83, 90 equals 261. 19. The final exam score is predicted to be 261. 19. The largest the final exam score can be is 200. Note the process of predicting inside of the observed x values observed in the data is called interpolation. The process of predicting outside of the observed x values observed in the data is called extrapolation. Try it 12. 11 data are collected on the relationship between the number of hours per week practicing a musical instrument and scores on a math test. The line of best fit is as follows. Y circumflex equals 72. 5 plus 2, 8x. What would you predict the score on a math test would be for a student who practices a musical instrument for 5 hours a week? In some data sets, there are values observed data points called outliers. Outliers are observed data points that are far from the least squares line. They have large errors, where the error or residual is the vertical distance from the line to the point. Outliers need to be examined closely. Sometimes, for some reason or another, they should not be included in the analysis of the data. It is possible that an outlier is a result of erroneous data. Other times, an outlier may hold valuable information about the population under study and should remain included in the data. The key is to examine carefully what causes a data point to be an outlier. Besides outliers, a sample may contain one or a few points that are called influential points. Influential points are observed data points that are far from the other observed data points in the horizontal direction. These points may have a big effect on the slope of the regression line. To begin to identify an influential point, you can remove it from the data set and see if the slope of the regression line is changed significantly. Computers and many calculators can be used to identify outliers from the data. Computer output for regression analysis will often identify both outliers and influential points so that you can examine them. Identifying outliers, we could guess at outliers by looking at a graph of the scatter plot and best fit line. However, we would like some guideline as to how far away a point needs to be in order to be considered an outlier. As a rough rule of thumb, we can flag any point that is located further than 2 standard deviations above or below the best fit line as an outlier. The standard deviation used is the standard deviation of the residuals or errors. We can do this visually in the scatter plot by drawing an extra pair of lines that are 2 standard deviations above and below the best fit line. Any data points that are outside this extra pair of lines are flagged as potential outliers. Or we can do this numerically by calculating each residual and comparing it to twice the standard deviation. On the T83, 83 plus, or 84 plus, the graphical approach is easier. The graphical procedure is shown first, followed by the numerical calculations. You would generally need to use only one of these methods. Example 12. 12 problem in the third exam final exam example, you can determine if there is an outlier or not. If there is an outlier, as an exercise, delete it and fit the remaining data to a new line. For this example, the new line ought to fit the remaining data better. This means the SSC should be smaller and the correlation coefficient ought to be closer to 1 or 1. Solution: graphical identification of outliers with the T83, 83 plus, 84 plus graphing calculators. It is easy to identify the outliers graphically and visually. If we were to measure the vertical distance from any data point to the corresponding point on the line of best fit, and that distance were equal to 2's or more, then we would consider the data point to be too far from the line of best fit. We need to find and graph the lines that are 2 standard deviations below and above the regression line. Any points that are outside these 2 lines are outliers. We will call these lines Y2 and Y3. As we did with the equation of the regression line and the correlation coefficient, we will use technology to calculate this standard deviation for us. Using the Lin-Reg-T test with this data, scroll down through the output screens to find S equals 16. 412. Line Y2 equals 173. 5 plus 483x2, 16. 4 and line Y3 equals 173. 5 plus 483x plus 2, 16. 4, where Y circumflex equals 173. 5 plus 483x is the line of best fit. y2 and y3 have the same slope as the line of best fit. Graph the scatter plot with the best fit line in equation y1. Then enter the two extra lines as y2 and y3 in the y equals equation editor and press zoom 9. You will find that the only data point that is not between lines y2 and y3 is the point x equals 65, y equals 175. On the calculator screen, it is just barely outside these lines. The outlier is the student who had a grade of 65 on the third exam and 175 on the final exam. This point is further than 2 standard deviations away from the best fit line. Sometimes a point is so close to the lines used to flag outliers on the graph that it is difficult to tell if the point is between or outside the lines. On a computer, enlarging the graph may help. On a small calculator screen, zooming in may make the graph clearer. Note that when the graph does not give a clear enough picture, you can use the numerical comparisons to identify outliers. The scatter plot of exam scores with a line of best fit. 2 yellow dashed lines run parallel to the line of best fit. The dashed lines run above and below the best fit line at equal distances. One data point falls outside the boundary created by the dashed lines. It is an outlier. Figure 12. 20 try it 12. 12 identify the potential outlier in the scatter plot. The standard deviation of the residuals or errors is approximately 8. 6 figure 12. 21 numerical identification of outliers in table 12. 6. The first two columns are the third exam and final exam data. The third column shows the predicted y-circumflex values calculated from the line of best fit. Y-circumflex equals 173. 5 plus 4 83x. The residuals, or errors, have been calculated in the fourth column of the table. Observed y value minus predicted y value equals y minus y circumflex. S is the standard deviation of all the y minus y circumflex equals epsilon values where n equals the total number of data points. If each residual is calculated and squared, and the results are added, we get the SSC. The standard deviation of the residuals is calculated from the SSC as letter 1D460 equals letter 1D446, letter 1D446, letter 1D438, letter 1D45B. Minus 2 square note, we divide by n, 2, because the regression model involves two estimates. Rather than calculate the value of S ourselves, we can find S using the computer or calculator. For this example, the calculator function lin-reg-t test found S equals 16. 4 as the standard deviation of the residuals 35, 17, 16, 6, 19, 9, 3, 1, 10, 9, 1. XY, Y circumflex Y, Y circumflex 65, 175, 140, 175. 140 equals 35, 67, 133, 150, 133. 150 equals 1771, 185, 169, 185. 169 equals 1671, 163, 169, 163. 169 equals 666, 126, 145, 126. 145 equals 1975, 198, 189, 198. 189 equals 967, 153, 150, 153. 150 equals 370, 163, 164, 163. 164 equals 171, 159, 169, 159. 169 equals 1069, 151, 160, 151. 160 equals 969, 159, 160, 159. 160 equals 1 table 12. 6. We are looking for all data points for which the residual is greater than 2's equals 2, 16. 4. equals 32.8 or less than 32.8. Compare these values to the residuals in column 4 of the table. The only such data point is the student who had a grade of 65 on the third exam and 175 on the final exam. The residual for this student is 35. How does the outlier affect the best fit line? Numerically and graphically, we have identified the point 65, 175 as an outlier. We should re-examine the data for this point to see if there are any problems with the data. If there is an error, we should fix the error if possible or delete the data. If the data is correct, we would leave it in the data set. For this problem, we will suppose that we examined the data and found that this outlier data was an error. Therefore, we will continue on and delete the outlier so that we can explore how it affects the results as a learning experience. Compute a new best fit line and correlation coefficient using the 10 remaining points. On the T83, T83 plus, T84 plus calculators, delete the outlier from L1 and L2. Using the Lin-Reg t-test, the new line of best fit and the correlation coefficient are y circumflex equals 355.19 plus 739x and r equals 0. 91.21, the new line with r equals 0. 91.21 is a stronger correlation than the original r equals 0. 66.31, because r equals 0. 91.21 is closer to 1. This means that the new line is a better fit to the 10 remaining data values. The line can better predict the final exam score given the third exam score. Numerical identification of outliers. Calculating S and finding outliers manually. If you do not have the function Lin-Reg t-test, then you can calculate the outlier in the first example by doing the following. First, square each y circumflex. The squares are 352, 172, 162, 62, 192, 92, 32, 12, 102, 92. 12 then. Add sum, all the y circumflex squared terms using the formula letter 1d6f4 letter 1d456 equals 111 letter 1d700 letter 1d4562. Recall that ye epsilon equals 352 plus 172 plus 162 plus 62 plus 192 plus 92 plus 32 plus 12 plus 102 plus 92 plus 12 equals 2440 equals SSE. The result, SSE, is the sum of squared errors. Next, calculate S, the standard deviation of all the y circumflex equals epsilon values where n equals the total number of data points. The calculation is letter 1d460 equals SSE letter 1d45b2 square. For the third exam final exam problem, letter 1d460 equals 244,011 2 square equals 16. 47. Next, multiply S by 2, 16. 47 equals 32. 94 32. 94 is 2 standard deviations away from the mean of the y circumflex values. If we were to measure the vertical distance from any data point to the corresponding point on the line of best fit, and that distance is at least 2's, then we would consider the data point to be too far from the line of best fit. We call that point a potential outlier. For the example, if any of the y circumflex values are at least 32, 94, the corresponding x, y data point is a potential outlier. For the third exam final exam problem, all the y circumflex s are less than 31. 29, except for the first one, which is 35. 35, 31. 29, that is, y circumflex greater or equal to 2. S, the point which corresponds to y circumflex equals 35 is 65, 175. Therefore, the data point, 65,175, is a potential outlier. For this example, we will delete it. Remember, we do not always delete an outlier. Note when outliers are deleted, the researcher should either record that data was deleted and why, or the researcher should provide results both with and without the deleted data. If data is erroneous and the correct values are known, e.g., student 1 actually scored a 70 instead of a 65, then this correction can be made to the data. The next step is to compute a new best fit line using the 10 remaining points. The new line of best fit and the correlation coefficient are y circumflex equals 355.19 plus 739x and r equals 0.9121, example 12. 13 problem using this new line of best fit based on the remaining 10 data points in the third final exam example. What would a student who receives a 73 on the third exam expect to receive on the final exam? Is this the same as the prediction made using the original line? Try it. 12. 13. The data points for the graph from the third final exam example are as follows. 1 5 2 7 2 6 3 9 4 12 4 13 5 18 6 19 7 12 and 7 21. Remove the outlier and recalculate the line of best fit. Find the value of y circumflex when x equals 10. Example 12. 14. The Consumer Price Index, CPI, measures the average change over time in the prices paid by urban consumers for consumer goods and services. The CPI affects nearly all Americans because of the many ways it is used. One of its biggest uses is as a measure of inflation. By providing information about price changes in the nation's economy to government, business, and labor, the CPI helps them to make economic decisions. The President, Congress, and the Federal Reserve Board use the CPI's trends to formulate monetary and fiscal policies. In the following table, X is the year and Y is the CPI. XY 1915-10, 1 1979-72, 6 1926-17, 7 1980-82, 4 1930-513, 7 1986-109, 6 1940-14, 7 1991-130, 7 1940-724, 1 1999-166, 6 1952-26, 5 2010-219, 2 1964-31, 0 2020-258, 1969-36, 7 2023-299, 2 1975-49, 3 Table 12. 7 Data problem. Draw a scatter plot of the data. Calculate the least squares line. Write the equation in the form y circumflex equals a plus bx. Draw the line on the scatter plot. Find the correlation coefficient. Is it significant? What is the average CPI for the year 1990? Note in the example, notice the pattern of the points compared to the line. Although the correlation coefficient is significant, the pattern in the scatter plot indicates that a curve would be a more appropriate model to use than a line. In this example, a statistician should prefer to use other methods to fit a curve to this data, rather than model the data with the line we found. In addition to doing the calculations, it is always important to look at the scatter plot when deciding whether a linear model is appropriate. If you are interested in seeing more years of data, visit the Bureau of Labor Statistics CPI website ftp//ftp bls gov/pub/special request/cpi/cpi txt. Our data is taken from the column entitled Annual AVG. Third column from the right. For example, you could add more current years of data. Try adding the more recent years. 2010. CPI equals 219.2. 2020. CPI equals 258.0. 2023. CPI equals 299.2. See how it affects the model. Check. Letter 1D466 equals minus 5030 plus 2. 598x. R equals 0, 90, 67. Is R significant? Is the fit better with the addition of the new points? Try it. 12. 14. The following table shows economic development measured in per capita income PCINC. Year PCINC, year PCINC. 1870 340, 1920 10, 50, 1880 499, 1930. 1170 1890 592, 1940 1364 1900 757, 1950 1836 1910 927, 1960 2132, Table 12. 8. What are the independent and dependent variables? Draw a scatter plot. Use regression to find the line of best fit and the correlation coefficient. Interpret the significance of the correlation coefficient. Is there a linear relationship between the variables? Find the coefficient of determination and interpret it. What is the slope of the regression equation? What does it mean? Use the line of best fit to estimate PCINC for 1900, for 2000. Determine if there are any outliers. 95% critical values of the sample correlation coefficient table degrees of freedom. N2 critical values, plus and 1 0. 997 20 953 0, 878 40, 811 50, 754 60, 707 70, 666 80, 632 90, 602 10 0, 576 11 0, 555 12 0, 532 13 0, 514 14 0, 497 15 0, 482 16 0, 468 17 0, 456 18 0, 444 19 0, 433 20 0, 423 21 0, 413 22 0, 404 23 0, 396 24 0, 388 25 0, 381 26 0, 374 27 0, 367 28 0, 361 29 0, 355 30 0, 349 40 0, 304 50 0, 273 60 0, 250 70 0, 232 80 0, 217 90 0, 205 100 0, 195. Table 12. 9. Stats Lab. Regression distance from school. Class time, names, student learning outcomes. The student will calculate and construct the line of best fit between two variables. The student will evaluate the relationship between two variables to determine if that relationship is significant. Collect the data. Use 8 members of your class for the sample. Collect bivariate data, distance, and individual lives from school, the cost of supplies for the current term. Complete the table. Distance from school, cost of supplies this term. Table 12. 10. Which variable should be the dependent variable and which should be the independent variable? Why? Graph distance versus cost. Plot the points on the graph. Label both axes with words. Scale both axes. Blank graph with vertical and horizontal axes. Figure 12, 23. Analyze the data. Enter your data into your calculator or computer. Write the linear equation, rounding to 4 decimal places. Calculate the following. A equals, B equals, correlation equals, N equals, equation, Y circumflex equals. Is the correlation significant? Why or why not? Answer in 1 to 3 complete sentences. Supply an answer for the following scenarios. For a person who lives 8 miles from campus, predict the total cost of supplies this term. For a person who lives 80 miles from campus, predict the total cost of supplies this term. Obtain the graph on your calculator or computer. Sketch the regression line. Blank graph with vertical and horizontal axes. Figure 12, 24. Discussion questions. Answer each question in complete sentences. Does the line seem to fit the data? Why? What does the correlation imply about the relationship between the distance and the cost? Are there any outliers? If so, which point is an outlier? Should the outlier, if it exists, be removed? Why or why not? Stats Lab. Regression textbook cost. Class time, names, student learning outcomes. The student will calculate and construct the line of best fit between two variables. The student will evaluate the relationship between two variables to determine if that relationship is significant. Collect the data. Survey 10 textbooks. Collect bivariate data, number of pages in a textbook, the cost of the textbook. Complete the table, number of pages, cost of textbook. Table 12, 11. Which variable should be the dependent variable and which should be the independent variable? Why? Graph pages versus cost. Plot the points on the graph and analyze the data. Label both axes with words. Scale both axes. Analyze the data. Enter your data into your calculator or computer. Write the linear equation, rounding to 4 decimal places. Calculate the following: A equals, B equals, correlation equals, N equals, equation Y equals. Is the correlation significant? Why or why not? Answer in complete sentences. Supply an answer for the following scenarios. For a textbook with 400 pages, predict the cost. For a textbook with 600 pages, predict the cost. Obtain the graph on your calculator or computer. Sketch the regression line. Blank graph with vertical and horizontal axes. Figure 12, 25. Discussion questions. Answer each question in complete sentences. Does the line seem to fit the data? Why? What does the correlation imply about the relationship between the number of pages and the cost? Are there any outliers? If so, which point S is an outlier? Should the outlier, if it exists, be removed? Why or why not? Stats Lab. Regression, fuel efficiency. Class time, names, student learning outcomes. The student will calculate and construct the line of best fit between two variables. The student will evaluate the relationship between two variables to determine if that relationship is significant. Collect the data. Find a reputable source that provides information on total fuel efficiency in miles per gallon and weight in pounds of new model cars with automatic transmissions. We will use this data to determine the relationship, if any, between the fuel efficiency of a car and its weight. Using your random number generator, randomly select 20 cars from the list and record their weights and fuel efficiency into Table 12. 12. Weight fuel efficiency. Table 12, 12. Which variable should be the dependent variable and which should be the independent variable? Why? By hand, do a scatter plot of weight versus fuel efficiency. Plot the points on graph paper. Label both axes with words. Scale both axes accurately. Blank graph with vertical and horizontal axes. Figure 12, 26. Analyze the data. Enter your data into your calculator or computer. Write the linear equation rounding to 4 decimal places. Calculate the following: A equals, B equals, correlation equals, N equals, equation Y circumflex equals. Obtain the graph of the regression line on your calculator. Sketch the regression line on the same axes as your scatter plot. Discussion questions. Is the correlation significant? Explain how you determine this in complete sentences. Is the relationship a positive one or a negative one? Explain how you can tell and what this means in terms of weight and fuel efficiency. In 1 or 2 complete sentences, what is the practical interpretation of the slope of the least squares line in terms of fuel efficiency and weight? For a car that weighs 4,000 pounds, predict its fuel efficiency. Include units. Can we predict the fuel efficiency of a car that weighs 10,000 pounds using the least squares line? Explain why or why not. Answer each question in complete sentences. Does the line seem to fit the data? Why or why not? What does the correlation imply about the relationship between fuel efficiency and weight of a car? Is this what you expected? Are there any outliers? If so, which point is an outlier?